Good morning, everybody. Thank you to the organizers for allowing me to poison a bunch of young minds about my favorite topic, subduction. And if you're sitting next to someone originally from France, you can see if they'll say this word for you, because it sounds a lot better in a French accent. So we'll go back to where Bruce began his talk with this typical mantle convection picture, an isoviscous mantle convecting, and you see these downwelling flows. The surface is being recycled. That's the cold surface boundary layer, and it looks fairly symmetric, and it's two-sided, and it's quite different from subduction, which is strongly asymmetric and one-sided. Okay, so this box here is about the size of that area we zoomed in, and so the major sort of issue has been that this is not really a model of subduction. They're distinctly different things, and they tell you about different things. So depending on what you want to know, you would either use a mantle convection model or a subduction model. So if you're interested in heat transfer, then convection is what you want. But if you're interested in the details of how this thermal boundary layer gets recycled and deformed, you would want subduction. Thermal evolution models, mantle convection is fine, but it won't tell you anything about the tectonic evolution, okay? Because the tectonics are intrinsically part of what's going on in the lithosphere and the crust. That's where the geological record is. And it's not really represented in a fluid dynamic sense. So we need to have actual kind of rocks to think about the rock record. And part of the problem is this plate bounding fault. It's a multi-scale, multi-physics problem, and this is where the tectonic plates are in the system. Why do we care about subduction? Because it's predominantly, this is an old cartoon of plate driving forces, and subduction is what is the major contributor to driving plate tectonics. This slab pull of the sinking slab is pulling the trailing plate. So this is the main driving factor for plate tectonics, and then there's some resisting forces in the system. This force here, the drag force, it could be either direction, depending if there's large currents that are producing the opposite sense of shear. But in this case, it's a passive mantle, and the plates are gliding over it, so there's some amount of drag. So we'll go into a little very basic introduction, so people understand some of these terminologies. And this is to scale. So you have a subducting lithosphere, and this is a good picture. The mantle's green, is olivine up here. So, and also this doesn't have a straight dip angle. You notice this is actually more correct because it's got a bending plate, which is a radius of curvature. So at any point there is a tangent line you would call the dip angle, but really on sort of upper mantle, in shallow upper mantle, we think about these more as a radius of curvature. Okay, so if we go to the surface and walk along a transect, here's the trench, sometimes covered by an accretionary prism, and as the sediments here and the slab dehydrate due to increasing pressure, there's specific pressures where the water is released by certain water-bearing minerals, and that promotes some lower viscosity in the mantle wedge. So here's a mantle wedge. There's a classic circulation there in the corner flow. We have some melting going on and generating arcs, magmatic arcs. So there's the arc. Anything between the trench and the arc is the forearc, and you'll have usually sort of some basin in there. Behind the trench, this plate is bending. It's a plate. We think of it as a viscous sheet or a bending plate, and so there's a little bit of an outer rise topography that's been measured, and it can be related to the bending moment. So the moment is sort of the weight of the slab that's bending this plate. And so it's producing a little outer rise there. And then in the back, this is an oceanic setting, for example. You can have a back arc spreading. Okay, so you can have an extensional setting that's drawn here. There's different settings you can have in the back arc, but the back arc is basically everything behind this arc. It can be extensional, compressional, continental, oceanic. So, and so I was looking on Google Images and found this nice picture of how subduction works. And so these are like the magnetic stripes, and it shows the plate just moving into the mantle along a straight line, and that's pretty much. So did everybody get it? That's how subduction works. I'll show it again. No. So who's moderating it? Do you have a moderator? Because I'm pretty much done here. Is the coffee ready? Snacks out? All right. Well, maybe this isn't how it works. We did have a few other questions when we started. I had this list of questions when I started to think about subduction. And some of the things that we were wondering, like, why do plates subduct the way they do? What controls the stability of the subduction zones? They're actually dynamic features that migrate and move around and create tectonics. How do subduction zones evolve? How do they interact with the overriding plate? How are these this system? How is it coupled together? So we think about this as sort of the subducting plate as the driver, and usually if it's a weak upper plate, like an oceanic plate, it's really the passenger, and it's responding to everything the subducting plate is doing. And then we were wondering, well, there's this global variation and radius of curvature. How is that generated? This is a complex function of all the dynamics in the system that's going to be determined by a lot of the material properties and dynamics in the system. And so these are the things that we were wondering. When did plates start subducting like they do? These are the things that are really captivating. You actually have to start to define what you mean by subduction. And I'll show you. It can get becomes a gray area. What do you mean by subduction? And how did plate tectonics operate in the past? Well, that's why we're thinking about deep Earth. We saw evidence, Mark Harrison showed, about subduction type environments already present in the Hadean. So what we need to do is Earth special, right? What we need to do is to actually think about, before we can really approach these, how well do we understand subduction on the modern Earth? How well can we answer all these questions? Do we completely understand it? And the answer has been no. And I don't think that it's really that fruitful to pursue speculating about processes in the early Earth if we can't actually come up with a predictive model for how plate tectonics is working right now and how subduction is working right now. So we need to figure out the present day where we have lots of observations. And then build upon that. We can have confidence to go think about the early Earth. And but I think we're right there. And if you saw the models in the talk by Jeroen, you can see that he's building on top of that foundation that we've just recently put into place. And so the time is exactly right to look at these questions. All right, so a little outline of what we're going to cover. Some kinematics of just what I mean by plate motions and trench migration. I'm going to show you a simplified model for the different ways a plate can subduct. And then I want to talk about a couple of key results. One is the trench curvature, how trenches develop. So there's a little fairy story about the Earth being like a ping pong ball. It's not true. And then the slab morphology, because we have people who really have spent a lot of time looking at seismic images. So maybe we'll try to make some sense of a few snapshots. And in terms of what it's a product of the trench motion on the surface interacting with this stratification of viscosity in the mantle. And then I want to show you just what the state of the art is in a couple different directions on subduction and how it's getting added into convection models. Okay, so a little bit of taxonomy, some stamp collecting. Probably not allowed in this holy house of theoretical physics, but we have a couple of different categories. So this is long ago shown as a Chilean type. So upper plates and compression, there's mountain building above a subduction zone. That's interesting. That's actually a pretty difficult thing to imagine, because it's the Chilean type. It's not that for an oceanic plate. How do upper plates can be in compression? In contrast, over at the Marianas, there's a back arc basin. The upper plate is in extension, so it's the exact opposite. There's a shallow dipping slab, some parts of along South America. And then over here in the Marianas, it's steeply dipping, so variation in the radius of curvature. And then this we can either have an overriding plate, which is continental in nature, or oceanic. And one of the things that gets driven home in that cartoon is that subduction's always happening underneath a continent. It's not true. A lot of subduction happens in the ocean between two oceanic plates. It's just a basic thing that people kind of get indoctrinated in, that all subduction is underneath the continent. And then this has a fairly fast-moving subducting plate, whereas this one here, the subducting plate is actually has a rollback component, and I'll show you what I mean by that. The other thing is it's interacting with the climate cycle, and we have places where here's a nice exposure of the trench along Nicaragua, and you see, okay, it's well exposed. There's actually an erosive margin here that they can measure how the subducting plate is grinding away at the overriding plate and tectonically eroding the margin. Whereas over here, it's not visible. Can't see it. It's covered by a big accretionary prism. These are sediments that are scraped off into sort of a giant sand pile wedge, and this actually feeds back into the dynamics. So these places typically exist where you have big rivers churning out sediments into the deltas. So one thing that's you can do very cautiously. I wouldn't. This is just something that's a bit of fun. It was a little controversial last time I showed it. So take those two types, and you can bin a lot of subduction zones on the Earth into one of those. And so one is based on sort of the upper plate strain, whether Chilean or Marianas, and whether you have a big accretionary system or more erosive. And the pattern has been that a lot of the ones falling into this little bracket here have been the ones producing the biggest earthquakes. So that immediately makes this connection that the large-scale dynamics of the system relate to the types of hazards and where places can be hazards. Of course, since this has been published, there's been a few earthquakes that don't occur in there that were fairly sizable on the 9 level. So for the kinematics, so this is our classic cartoon of a plate. So let's imagine a hot spot here. Plate moves forward some distance. That's immediately translated into an amount of the slab going into the earth, just like that cartoon would show. So the trench here is stationary. There is a way that a plate from the surface can enter the mantle, which is with a component of the trench retreating. So here the trench has retreated a little bit, and all that's happened is the slab sunk by gravity. Gravity pulls the plate down, and geometrically what happens is the trench moves backwards. So it's really that simple, and you see the outline of where the slab used to be. So this is what we refer to as slab rollback, and that accommodates trench retreat. So notice that some amount of the plate that was on the surface has now been recycled into the earth without the plate having to have moved forward. And in this case, there's also a component of forward motion. And this is how plates actually subduct, is with both a component of forward plate advance and slab rollback. You can have places that have stationary plates and can recycle the entire lithosphere, the entire plate recycled through slab rollback. It actually turns out to be one of like the default mode, if you want. You have to have something other special happen in order to do this. So any other planet, and it's actually been proposed for Venus, that you do have slab rollback and large back arc basins. All you're doing is having a trench retreat and create a large back arc basin. And this has been proposed to happen on Venus. And this is what, if you did have subduction on other planets, it would probably be in this slab rollback mode. Yeah.
Talk about it. You gave us a diagram of a Chilean type of Mariana type, and then you showed us the contrast between Central America and Southwest U.S. And I've been watching this, and I wonder, are there typical subduction zones, or is everyone different?
I'm going to show you there. I think each subduction zone is sort of an individual that needs to be considered in those kind of terms. Yeah. And within we do have a population that we can investigate, and that's what we use actually to try to understand the range of behavior within these models. So I'll show you kind of the next. I think we're two slides away. The standard answer, right? No, it's just that they're sort of when you study these systems in a general sense, you find that if you have temperature dependence, the default thing a planet would do is have a stagnant lid. It would not have plate tectonics. It would generally have a stagnant lid. You need something else to happen in order to generate a sort of recycling a lithosphere. You need something even more special to happen to generate plate tectonics, because that's a subset of mobile lid tectonics. Okay, and then with subduction, the default mode is probably just sinking of a plate, and that would produce slab rollback. So I'm trying to frame the concept of subduction in terms of the thing that was a default mode is actually the thing that we typically don't think of as subduction. In the same sense that if we think about a planet recycling its lid, we think of plate tectonics, but this is actually kind of a special case.
The default mode is because we have horizontal transport on the surface, which seems to me maybe hard for a planet to avoid. If it starts with default mode, some component of the horizontal transport has to enter.
It doesn't have to, but I'll show you that it does, and now we understand why it does, and to what degree. So it doesn't necessarily have to have a component of forward plate motion, but it does. And the reason is, how much does it have and why? So now we understand that. So I'm going to show some plots that depend on... Oh, sorry.
Another observation here, though, is that the trench has to sink, which implies that it's denser than the underlying manifold.
That the plate has to sink, yeah.
There are situations where that's not going to be true, like the moon, for example. So if you end up with a crust that's buoyant.
Yeah. You need a net negatively buoyant lithosphere.
That may be a key feature of the Earth, the accessibility of the equidistant salt transition.
Absolutely, and this is where the petrology, the net buoyancy is that we have. The planets can readily generate negative buoyancy from cooling, but because of composition and melting, they generate positive buoyancy that act to keep the plate at the surface and reduce the net buoyancy. And so Rick's exactly right. The compositional aspect is a huge consideration in the net buoyancy of a plate, and whether it will even want to sink. And then that will vary with age as well, because that's where we get the longer it's at the surface, the less negative buoyancy it'll have. And Bruce showed some of that work of your own in the end of his talk. Okay, so was there another question? Yeah.
In terms of the relative
Relative velocity between the plate and the slab. They're geometrically related. So the slab is sinking here and the plate is moving there. So there's just a trigonometric relationship between them. Yeah.
I'm just wondering if each of these cases might not be represented as the relative velocity between the two.
Between two plates.
Yeah.
Yeah. That's true. I'm gonna touch on that. So. Okay. So for these depend on the reference frame that you're using. Okay. And the subducting plate velocity is sort of relative to other plates or the mantle. And so I prefer to the mantle reference frame as the absolute reference frame, and the plates are moving above the mantle instead of relative motion between two plates. And I just try to pick a mantle reference frame because that's easy when you model things. Your box is stationary that you would model something in. And then the trench as well. So this shows in two different types of back arc environments. You can have forward plate motion. You can have trench retreat. There's the outline of where the slab was previously, or you can have even trench advance in some cases. It's possible. And then the subduction velocity, okay, is the combination. This is the rate at which plate material is recycled and removed from the surface. So if you combine the trench retreat, which is making the plate disappear that direction, and the forward plate motion, which is making the plate enter the mantle and disappear in that direction, you combine those, that's the total subduction velocity. So that's the rate that the plate's disappearing from the surface. Now these depend on the reference frame that you use. So if you don't have an absolute mantle reference frame, which is actually a difficult thing to find, we think we have one now that's essentially centered on Africa being stationary. And if we adopt that, we get a picture of what the kinematics, and I'll show you what the global kinematics of these plates and the plate boundaries are. If some things are independent reference frame, okay, convergence velocity, so one plate moving towards another and this rate that they converge at, that's independent of what reference frame you use, and so is the erosion and accretion rate, because this is local to the trench. All right. So, yeah, Bill said this, well, is there a typical subduction zone? Well, no, they're all doing something different. In this reference frame, we count about 24 different subduction zones, and they're color-coded here as the ones that are retreating. So, for example, up here in Tonga, it's retreating at a rate of about 16 centimeters per year, so the units here are centimeters per year. That's almost double the speed that any plate is moving. But we're still subducting things at that rate. Typical plate speeds in this reference frame, notice they're about 8 at the most. Some places 7 is a typical number for a subducting plate. And a lot of the plates that are attached to subducting slabs actually have about 7 as a typical subduction plate velocity. Okay, and that turns out that's also the typical sinking rate for a slab in the upper mantle. So here the Juan de Fuca plate is stationary, but these little arrows, these black arrows, also indicate the rate of trench migration. So there is a component rollback there to 2.2 centimeters. That's our local subduction zone. And then a few places, very few, are in compression, have advancing trenches, and so that's at the Bolivian orocline there. But predominantly, it looks like they're mostly retreating or stationary. Okay, and that's pretty interesting. So they range in. So one thing that seems we found is critically important is the width. So if you looked at this is about 6,000 kilometers in lateral extent. 6,000 kilometers, very wide plate, and we have little tiny ones over here that are only about 200 kilometers. And so they actually will have, they tend to have different dynamics. And the pattern that shows up, this is exaggerated because of the projection. So Scotia is actually pretty small, a narrow subduction zone, and similar to that, and the narrow ones tend to be the ones that retreat. And the wider ones, the ones that have the largest extent, tend to be stationary.
That makes sense, doesn't it? Because when you're retreating, you have to get fluid out of the way.
Yeah.
So you have to flow around the edge or
Somehow
accommodate the change.
Intrinsic in this is the fact that they have edges and they're finite. And so everything here shows edges. And seismologists have shown many times in up here, this corner, some places here, and definitely here, and also here, they map flow through seismic shear wave splitting. And they can see this sort of flow of the mantle coming around these slab edges. So we know that the slabs have edges. I see a hand there, but it's just blinded. Oh, it's Ed.
You have to be careful in that kind of language. The seismologists map shear wave splitting directions, fast directions, slow directions.
And then think that it means flow.
Well, then the rest is interpretation.
Yes. I was sloppy there. Sorry.
Well, I'm not trying to bump your chop.
You're exactly
just
correct.
a little bit. But I mean, it's and maybe, I don't know, Doug or Barbara might talk about this, but as you know, the subduction zone environment is not a plane layered situation, which is the technology used to get the shear wave splitting. And near the edge of a slab, it's complicated. It may turn out that that's the only way to explain those data, but nobody's really demonstrated that, in my opinion.
In some cases, there's geochemical.
Yeah, I was just gonna say that over here there's.
Technology is really important, but it's not.
Over here is a good example. There's the Samoan plume right here, and as this opens up like a saloon door, it used to be over here, and it's been opening up just like a saloon door. We in models show it's induced a flow to come around that corner, and it's been dragging some of the signal identified by the Samoan plume into that Lau back arc basin and polluting the back arc basin rocks. And so, that's a really strong indication that there is a toroidal flow, and the studies there of seismic studies corroborate that is a thing is going on. We do not know the depth at which it's going on, and they're integrating a signal through a large amount, but it's getting a signal of that kind of circulation around a slab edge really well.
Actually, a seismic study is needed there. Nothing is really corroborated yet. The whole northern region of the Lau Basin hasn't been occupied with stations. Northern Lau Basin.
It's also there's a good study here. There's a geochemical and I think there's a seismic study there.
Well, the study in the Lau Basin is a little bit further south from the northern area, but that's long, strike, fast, and flexible. So we kind of infer that in the northern part is probably the direction of flow. Then the geochemical signal is kind of complicated there, right? So.
I guess this is maybe you're going to go here with some of this. I always struggle with understanding. Let's say there is flow around the edge of a slab. It's a bit of a chicken and the egg, because let's say the mantle is conspiring to enable the slab to roll back a little quickly in that particular spot, and maybe the flow is already in place on the side of a slab, and so.
Yeah, we'll show you some models that it's not quite it's a chicken and egg as it might appear. It's the sinking of the slab induces that flow to occur, which then feeds back and continues to. It's a positive feedback established, so that the two amplify each other and allow both things to progress. But the slab's the one that's driving, because it's the buoyancy force. So.
But it's in a flow field already.
It's in a flow field, but it's the most important buoyancy source from miles. So it's going to dominate anything else around. Everything else is, there's ambient circulation, but concentrated buoyancy of the slab is going to induce a flow. It's going to be the most important thing in determining the flow. Yeah.
You've seen these tank models from Crispy K and Kelly Drew, and they're looking at subduction in the presence of a plume.
Yeah.
Basically, the flow induces
Yeah.
With all sorts of different things. So
Yeah.
it's the slab that's the 500-pound drilling or mantle flow.
Yeah, I don't have time to show that stuff, but I'm an author on the paper, so I know the work. Yeah. Yeah, opposite curvature. Very good observation. He's noticed that this has the opposite sense of curvature as a lot of the other slabs. So I'm really glad you pointed that out. It's key. So anyway, these things evolve. These are, we also have to recognize these are current velocities, and the shape and the amount of the velocity has been changing over time. This is a time evolving system, and this is a snapshot, okay, that we see right now. We can see some of the history and the evolution if we look into the tectonic record, and that's what we need to be able to do. So now I'm going to attempt to average the kinematics along a particular subducting plate, and it is you have to be careful about what you include in the average. So what I want to do, for example, there was a lot of lateral variation you saw in the trench retreat rate in the Tonga-Kermadec system, huge, and so how much you include is going to change the average. Okay, so but we kind of looked at some of these different scenarios, and we found that we wanted to look at a variety. So we took about 16 of these subduction zones, and they're color coded here as to their names, and then we plotted their subducting plate. So how fast are they moving in that reference frame that we think is the Mantle reference frame? And there's this interesting seemingly correlation. There's a few outliers here, but it seemingly correlates with the width of this of the plate. So this means that the fastest, the widest plates are the ones that are moving the fastest. And you see there's this upper limit here of about 7 centimeters a year. There's not that many plates that are moving faster than 7 centimeters a year, and that's our estimate of how fast a slab would sink in the upper mantle. So that's a consistent story. So here's what I mean is that this is the Aleutians, and that blue line, the length of that line, is the width of the subducting plate that's going down there. We can also measure the trench retreat rates, and the trench retreat rates tell the opposite story, that the speed at which the trench is retreating, remember this had a large component of trench retreat, is and that's why it's so variable that it does not come anywhere near this line. But the other ones that have less variability along trench tend to show a trend where the fastest trench retreat rates are the ones that are the most narrow, and the ones that are the widest have very little trench retreat. Okay, so and also here's that 7 centimeters per year. So if you only have a super narrow trench, a super narrow plate, it will probably subduct entirely through that slab rollback. So there's a strong function of the width of the subducting plate from modern plate motions. Well, you can take the ratio of these. So we can take the ratio, add them. We can take both components. So that's the total subduction velocity that I showed you. That's both the plate motion and the plate boundary motion. And so this is the speed at which things are being removed from the surface. And just look at the part that is by the subducting plate motion. Okay, so this is the fraction that's a subducting plate, and the fraction has this nice relation with plate width. And so what you see is that so a fraction of 1 would imply that it's entirely subducted through forward plate motion, and a 0 would imply that the plate is subducting entirely through trench retreat. And we see a strong dependence on the width. Okay. Yeah. This is the present day. present day snapshot of what's going on. We don't have measurements for the past. Yeah.
How did you
Yeah.
define those segments? For example, if you look at the black one,
Uh-huh.
it spans several,
Right. Yeah. For that one, it's not as clear cut, but we're trying to identify regions in there that would indicate like a segmentation, and there are places where it appears broken, but it would have to be broken big enough so that a huge window is opened and mantle material can freely come and go in between the two segments, and we didn't see anywhere along there that you could have a total decoupling of the one segment to the left. So this is actually 3 distinct subduction zones. This is Japan and Ryukyu, and then down here Nankai and there's Nankai, Ryukyu. So this goes up to Kamchatka. There's a whole that's a definite slab edge there. But anyway, yeah. So there's.
so this is based on what, tomography?
It's based on tomography essentially, but it could. I mean, this is a first order. It needs more detailed study to really interrogate if these are the exact segments that we have.
So if you broke it up, that symbol would go up off the plot.
If we change this one here, let's see so I think that one is
It's the little upside down triangle.
it's that guy there,
Yeah,
which is.
it's on the axis. Right up at the top.
There he is. Right, there he is. Yeah, he's off the line. So if we broke it up, yeah, it could be 2 smaller ones that are over here. Could be.
Were you able to measure the Caribbean Antilles?
Let's see, Caribbean. Lesser Antilles is there. Which one?
I just didn't see it on the. You don't have a black bar.
Not. Yeah, I haven't put it on the black bar. So. Yeah, I'm not seeing it. So, okay, one more question, Jackie.
If I look at the plot, velocity versus width, so below 1,000 kilometer, there seems to be no correlation. The velocity function is anywhere. You can have a horizontal, vertical line, and above you can almost have a horizontal line.
Okay, so in this region here,
That's right.
yeah.
What's the physics behind the curve that you put in? Look, the R value looks kind of okay.
Yeah.
I don't know how you decide.
I agree. It's imperfect to try and get this part of the curve. It's sort of pinned more by these, but then there's these outliers here. It could just be a straight line across if you want. But I'm going to show the physics, but we have only gotten through part 1. So I want to explain this partitioning, and with a simple model here. And so in contrast to mantle convection, the mantle convection has a surface thermal boundary layer, which is negatively buoyant. And then taking into account the amount of crust that we have currently, which basalt is buoyant, and we have a net buoyancy. So we just write this we just prescribe the density and say we know it's this negatively buoyant relative to the underlying mantle. So we've simplified the thermal part of the problem into just a compositional buoyancy in a lithosphere. And so this is attempting to capture the essence of subduction of a unstable mechanical sort of plate, which we can represent as a viscous sheet. Viscous sheet works pretty well. And so there's the plate motion. We're going to measure the trench motion. And so we have a small box with it's 1,000 kilometers deep, and it has a small amount of the top part of the lower mantle that's more viscous. And this interface here is a viscosity interface. It doesn't have any phase change or something, but it would be sort of part of that barrier to flow here is the way to think of it, whether it's a viscosity increase or phase change. And so here's that toroidal motion around the slab edge and the sinking velocity of the plate and the rollback velocity and then the total subduction zone. So this is the typical model setup. It's actually, this is a numerical version, but the first ones that were done were these fish tanks where they used honey or corn syrup and a silly putty for a plate. It worked remarkably well to, as analog for the upper mantle, for a plate subducting the upper mantle. And this model setup has been used for numerical models and laboratory models and semi-analytical, like boundary element models. Neil Reby has been doing, and they recently all had this kind of confluence and agreement, independent of the method. But I'm just going to show you this stuff because I had these figures ready. But there's a large number of workers that have done important work. Just a description, this is that same momentum equation that Bruce showed you. There's no inertial terms. And we're representing, instead of that delta rho being rho alpha delta t, we've just prescribed essentially a delta rho that we think is appropriate, and then conservation of mass. So there's no heat transfer in this. We've subtracted that out. We have added in a brittle crust here, which will have a yield stress. So when we describe after something has been yielded according to some critical yield stress, it will have the lower of the two, and then we write that as an effective viscosity. And I just wanted to show what we've empirically, through tweaking these models to make them look like Earth, and also with our sort of intuition, described this as a brittle crust with a strong core underneath and a creeping section underneath. And the part that's relevant for bending is the width of this strong core. It actually depends on that thickness there to the cube. So it's critically important how wide that strong core is as to whether the plate will be easily bent or not bent very much. And then this is actually very consistent with using laboratory-derived empirical relations for different types of viscosity, including the Byerlee law, high stress plasticity like Peero's creep, and a normal sort of ductile temperature-dependent creep. And the weakest one wins. So if you look at this 80 million year old plate, which is kind of the thickness that we've been assuming, that gets down to around there, there's a creeping section, a strong central core. If you just adopt some, say, everything above this is strong, this particular stress, and then everything here is weak. And so we've basically done a step function of weak, strong, weak in this. Okay, so, but it is consistent with laboratory experiments.
The velocity vectors are bothering me on that slab rollback for some reason.
Because it's drawn by an Italian, I think. Yeah.
But isn't the net velocity to the left?
The net
The
velocity.
plus the slab velocity add up to something that points to the left. Those two dark arrows pointing downward.
These guys.
Yeah.
That's sinking. This is the trajectory that that little parcel of fluid is going to have going. It's sort of down into and back behind the slab. So that's the sinking trajectory of that little parcel of slab. Doug.
Dave, in these kind of plate bending realities and so forth, don't you decrease the thickness of the strong core as you bend the plate? In other words, as you saturate the brittle crust part, the traditional idea is that the elastic core becomes very, very thin as you bend the plate. So therefore, the strength of the plate actually decreases greatly as you bend it.
I think that's right, and I think that this whenever you look at a strength profile, you've got to remember that this is a maximum best estimate of strength, and there's always other things in nature that act to reduce the strength. So this is always a best case scenario, and slabs going through a bending region definitely get damaged, in ways that aren't captured by these like laboratory experiments at the micro scale. So the mesoscale strength here, what the effective viscosity is from the compilation of effects, the net, all these things that you're mentioning. For sure, these are kind of upper bounds in my mind.
Another point I think, Doug, is that the elastic core in these plates is probably the only inner kilometer. Everything else exceeds the stress.
Yeah.
So part of what gains is elastic strength. It's a tiny bit.
Yeah.
Yeah, so there's a time scale issue here. This is appropriate for, it's appropriate to think about a plate as a viscous sheet on a time scale of millions of years of a subducting plate. And we can't really access that if we just look at elastostatics or elastodynamics of a modern day Earth, because we're looking at time scales that have that elastic component in them. So this is a different time scale.
Because we do see earthquakes, in the trench region going through.
Their earthquakes are happening on an elastic time scale. So this is the representation of how the plate works on longer time scales. So it's separated from that.
Well, no, but if you have an earthquake going through there, it relaxes the strength. So
It breaks it. Yeah. It's breaking it. Yeah, and damaging it. Yeah, and that needs to get factored in there. And so when we do this, we actually leave the total strength as a free parameter to try to understand what the effective viscosity should be. We're not taking these laboratory things literally and then applying them blindly. We're actually leaving all these things as free parameters to see which ones produce Earth-like subduction, and then the net we get effective viscosities in which the net viscosity is some summation of effects, including ones that you're mentioning that aren't represented in the other conventional means. So these models don't prescribe anything. They're not imposing where the trench should be, how fast the plate needs to go, how fast it needs to converge. They're letting the buoyancy decide everything and the strength of the plate. So there's the only two things that are specified, and everything else is free to find out what its value should be, including trench retreat rate, convergence rate, plate speed, radius of curvature. All these things are emergent from the dynamics in the system. And so like I said, we don't have heat transfer in this problem because we've tried to capture the essence of convection just as represented in this negatively buoyant sheet. And we've got a Newtonian mantle. It's not totally accurate, but we think about things as effective viscosities that encapsulate lots of other physics that we don't have. And we don't have an overriding plate. So with big continents, okay, this is going to dominate what the subducting plate wants to do. But in the absence of a big continent, the subducting plate can decide these things. So that's the best way to think about this is we've got a weak oceanic overriding plate with a back arc basin. It's back arc spreading center, which provides very little resistance to the system. Okay, so that's the closest thing in Earth that would be analogous to this. And then there's that important toroidal flow that comes around that edge, and this is observed in all the laboratory models and numerical models on both sides. So this is the toroidal flow, and it actually, part of that wedge circulation and the classic corner flow that you would have, this corner flow here that we've had since the 70s, it gets swamped out by this horizontal flow coming around, because this flow is driven by pressure gradients, and pressure gradients are established between the subducting plate and the overriding plate. However, when you have slab edges, this flow comes in and kills those pressure gradients. So this strongly diminishes the amount of classic corner flow circulation along that. Yeah, Michael.
Would you really kill it, or not? Shouldn't you literally be superimposing that corner flow and the flow around the edge?
It's not killing it, but it does help. Right, but the pressure difference, the hydrodynamic suction, is driven by a low pressure on top of the slab and a high pressure on behind the slab, And this allows these two pressures to talk to each other and equilibrate, because you can have flow come from the behind the slab to the front of the slab this other way. And so that helps re-equilibrate the pressure from in front of and behind the slab, and that decreases the classic kind of hydrodynamic lift that's going on. No. There's no lift.
Anyway, it doesn't matter.
Okay. Okay, well, as this slab sinks, this is what Ed was referring to, that there's this chicken and egg apparently, but it's the subducting slab which induces this flow, which then pushes and deforms that plate into a curved surface, and that curved surface is expressed at the surface of the Earth as trench curvature.
I just want to clarify, if this is the chicken, my egg is it's outside this box. I agree with what you say. The slab's the game here. The slab's determining the flow. But if you have a lot of, like, let's take something 5 times bigger than this box, downwelling, and it is very viscous, plate coupled to mantle flow, you have return flow. That might be on the down dip side. That, anything you push down, stuff's coming up. And if the current is to be pushing towards the slab as it's rolling back, it's facilitating the rollback process.
Yeah, these things are not happening isolated. In these experiments, they're happening in an isolated box, but they're happening within the context of a global circulation. However, the uppermost part of the mantle is highly non-Newtonian, and so these, if you think about, if this is for a Newtonian this is streamlines in a Newtonian fluid, what happens is in non-Newtonian fluids, these would bunch up to be closer to the edge and respond more quickly and more locally to the buoyancy source of the slab. So this effect would basically be compressed in closer to the slab, and then it's almost shielded more from the large scale circulation. Yeah. If I get to that, I want to show you a flat Earth first, okay? Because the point is that it's not, the curvature here is not a product of the spherical geometry of the Earth. It's a product of this mantle flow and the stresses that coming around and pushing, deforming the slab, dominate that any kind of sort of spherical sort of ping pong ball pushed in bending stresses. So these are some numerical models, and there's a symmetry midplane here, and I'm showing the second invariant of strain rate, which you could think of as deformation. So when it's pink, it's got no deformation, and when it's so it's there. And when it's sort of red and darker, there's high deformation, high strain rate. And we have sort of a proxy for this is looking down. The 660 is represented by this gray surface, and we put a big box in there so that our boundary conditions don't influence the flow that's induced. So all the flow is induced locally here, and this is a perspective view. So the plate there's a mirror side of this plate, so it should actually be kind of a plate that's this thick, and we're only modeling half because we're exploiting that symmetry. And this is the initial length of the plate, and this is sort of the ridge. This is the tail of the plate. And we started with a little tiny perturbation so that it wants to start sinking. Did that answer your question? This edge, that is the edge. Yeah, so there's no overriding plate or neighboring plates. This would essentially be like a giant transform fault, like a step fault with, like Scotia or something like that. The plate, this is all sort of free slip surface where there's no plate. Yeah, so recent models have been putting plates in everywhere. But we want to look at finite width plates. So I'll show you the evolution here. And you see that the plate's moving and the trench is retreating. And the trench is developing curvature because that flow is coming in and deforming the slab, which is then expressed at the surface as trench curvature. So we're developing appropriate sort of trench curvature on a flat Earth. That's a viscosity interface. It's not so that it's originally flat at 660, but as this slab begins to pond on it, it starts to depress that interface. Yes, there's only viscosity in here. 100. Okay, so we saw that the plate started out this big and it ended up that big. So the difference is the amount that got subducted here. And it moved this far in the experiment. And the trench retreated that. So it actually subducted more by trench retreat than by forward plate motion. Okay, and that's what we see for plates on the Earth. I can't explain it any more simply.
So let's do like a real world thing where I have maybe a saran wrap or a towel or something in a bathtub, and I'm pouring into the bathtub and I'm pulling the towel back. No.
How do you bring the towel back?
To induce this rollback.
Okay, so canoe paddle. Let's think of this. If this was a really strong plate, then this would be a canoe paddle, and you'd be sort of driving, flow around like with a canoe paddle. But this is a deformable canoe paddle. It's only just slightly stronger than the.
Towel or
Yeah.
Instead of a big plank of wood.
Right. Yeah.
Okay, I just want to imagine this thing caving in and having a concave sheet as I pull it back.
Well, it's pulling itself under its own weight, and that flat flow is coming in and inducing the central sort of indentation. So this changes when you have a wider plate. Okay, so now the plate is actually off. The other side is off the screen here, and this toroidal flow really only affects the edge of the plate and the central part of the plate. Basically, if you look through a cross section there, this part of the plate is approximately 2D. So that's where that cartoon representation is appropriate. But over here at the slab edges, you get variable amounts of trench retreat, and so the entire plate is moving forward. And this one's had a different amount of plate. So this time the plate is a little bit further, and we subducted more by forward plate advance than by trench retreat. So there was less trench retreat, and the original position of the trench is closer, so it's becoming more stationary, like we saw in Earth for very wide plates.
You made the comment that the power law rheology localizes the stress strain. Would you be able to sort of distinguish the different rheologies by the sort of structure of that slab?
I think you could in principle, you could include nonlinear rheologies in the mantle, and then include what you think is the best representation of the mechanical plate, and then look at this curvature, and then try to infer what the real effective. You could start to back out what those power law relations are, the activation energy and things like that, and the power law. From if you did that, I think that people will eventually do that, but I don't think it's one of the big. It's not any of the big game to go after right now.
Just curious, what's the equivalent length of time of the amount
Okay,
of calculation you showed? And then the follow-up question is, what happens if you let the calculation keep going?
Yeah, if we let the calculation keep going, this is going to subvect all the way down and make a big pile, and that pile is going to sort of sit there for a while and then flush into the lower mantle if we had more of a lower mantle. Time scale of this experiment is about 30 million years, but the sinking rate for what this plate at the surface to sink to that boundary is less. It's about 8 million years. There's not a lot of diffusion happening in that time, which is why we've sort of neglected diffusion, because we're just looking at the sinking of the blob going from there to there. 8 million years. It's approximately not changing. Timo.
Plate velocities that you are seeing somewhat consistent to reality?
Yeah, so we're pinning this to 7 centimeters your sinking velocity, and we're getting a partitioning of plate. That 7 centimeters can either be through forward plate motion or trench retreat, depending on the width.
So the shape of the slab develops in this concave
Yes.
So, given the curvature, can you then solve for the viscosity of the plate?
Yeah, that's similar to what Bruce was saying. I mean, is you have to think both the plate and the induced flow and get both viscosities right. So, yeah, if you want to match exact details, then you can pursue that. This is just trying to get the first order question of trying to generate the partitioning in the types of motion. Okay, so if we go back to those experiments, these are slab motion, trench motion, and the partitioning. Okay, and getting back to Jackie's question, these are our experiments, and yeah, we don't get a good agreement on that side of the slope either. But we do have these lines here are fluid dynamic scaling, which is based on the sinking of an oblate ellipsoid. And what that takes into account is the varying amount of drag on the system, depending on the width of the oblate ellipsoid. Then if it's wider, it will partition that drag. The different component amount of toroidal flow compared to the poloidal flow will change the amount of the drag on the system, and that's essentially the physics that's controlling the overall trend. Now, yeah, there is a similar sort of imperfectness down there, but on the models remarkably look like what's going on for the Earth. And so this I would claim, is one of the first ways to give us confidence that our ideas are right. We're thinking about the plate in the right way, and we're generating a spectrum of behavior for that's observed for the Earth with a simple model. And so this is really the first way of describing plate motion in this way, is driven by slab pull, because that's the only thing in there.
But to come back to Ed's question or comment, the deviation away from the model in the real Earth could indeed be the large-scale circulation of the mantle.
Yeah, especially these guys.
Yeah.
Yeah, we've got some other things to figure out still. Timo had a question.
But that makes sense. On the left side, the width is not very big, so it's not dominating the situation. Whereas if you're on the right of the picture, then the slab is so big that it's just dominating the behavior.
The theory might work a little better on this end. Yeah. Question in the back. Yeah.
But I think in the classical theory of tectonics, in the spherical Earth, there is a relationship between the conduction, the trench width, and the conduction angle. It says if the trench is wider, and then the conduction angle will be deeper. I'm wondering whether the teaching angle will play a important role.
Are you talking about sort of an east-west difference in the subduction angle?
Not east-west difference. There was a book called The Fundamentals of Geodynamics. It says some theory like the spherical Earth is like a ping-pong ball.
Yeah. Ping pong ball. Okay, now we're on the same page. All right. My last talk was ping pong ball, and I can point you to some other things at lunch. I've got just a small amount of things about ping pong ball in here, but yeah. Okay, so question is, was this representation with these plates a myth? Does it not work? All these things right in the textbook, the textbooks could be wrong. Well, maybe. It's not as easy as it's tooth fairy, okay? So, yeah, so we don't know. I would say that this one, at least for now, this myth is busted. Okay, the other ones, I'm going to say something. Easter Bunny, we got to work on that a bit more. So, all right, I'm going to start skipping some slides now. Okay, ping pong ball. So there is this ridiculously smart guy at Mahidevin who started thinking about, what Earth would really be in terms of a ping pong ball, and you can develop these sort of dimpling instabilities. So this is sort of like equivalent of a subduction zone, and these would be these dimples on a ping pong ball. You would have equivalents of a trench, and so this is this Frank paper trying to explain why the subduction zone curved. But what you had actually mentioned earlier, that we can just stop arguing right now, because South America is curved in the opposite direction. Remember, in the Bolivian oricline. Okay, ping pong ball over. And why is that? It's because these bending stresses. So this is a dimpling instability based on the material properties of the slab. It's subducting into sort of free space. There's no coupling or interaction with the underlying mantle. So there's this toroidal flow is not interacting with this subduction with the slab edge, and that's the essential physics that's missing from this. So I mean, this is a proper way to describe the instability of these in this geometry, but it's not relevant to the Earth, because along South America, you notice that the curvature is in the exact opposite direction, and so and we need to be able to explain some of these are curved quite variably along the trench. So they don't look anything like a simple dent in a ping pong ball. Okay, so very quickly, those initial trenches that we had, they evolved to more curved. So when you have narrow plates that are sort of just 1,000 kilometers or so, we see this in plate reconstruction. So the Scotia plate started off and progressively retreated backwards and became more curved, and then this is the example for the boot of Italy that has been, the Mediterranean is a big back arc basin that's rolled down and then formed that. Italy is an arc, and it's a highly curved arc. So we see this, if we look at this, it starts off with a straight trench and develops into a nice curved. So the narrow plates have retreating trenches, become more curved over time, and notice that because there's this viscosity interface, you get a flat-lying slab there, and I'm going to talk a little bit more about that. Okay, and then there's the stationary trenches. They tend to be more stationary and more quasi-linear, and so it's more quasi-stationary trenches. So let's skip because we saw that one, and this is what one that might be a factor is that you have edges here, so you have some amount of trench retreat, but in the center you have a high pressure system that's approximately 2D there. So these models I showed you to emphasize the fact that it's mantle flow dominating the system. This induced flow is dominating the curvature that's developed. But this is also done in spherical geometry. This is a work by Gabriel Mora, and they find amazing similarity for the models that all the physics, including that partitioning that I showed you, it actually falls out of these systems in spherical geometry as well. The same partitioning that we found with you use similar material properties, and they actually generate, just with these simple sheets, they can generate patterns of plate motion that largely agree with the observed pattern. So that's amazing, because it says the plate motions on the surface are predominantly described by sinking slabs attached to plates.
Okay, so there's no continents in there?
There's no continents. They're just they're just viscous sheets. Okay, so there's actually a whole, if you aren't trying to just exactly zoom in on the ones that are relevant for Earth, there's a huge spectrum of behavior that's possible that you could speculate would be relevant to other times in the Earth or other types of Earths. And there's a giant number of talented people that, I've just given my version, but there's been a lot of really excellent work by a lot of people that have really helped build this foundation. So real quick about the slab morphology. This is some cross sections through a couple of different regions on Earth, and you see, okay, it always looks something different. This one's going backwards. This one has how these things, they don't really look like nice continuous blue sheets descending in the mantle, right? Something is wrong. And then you've got some of these that sort of fan out as you get into the lower mantle. Okay, so there's a lot of variability. And we saw in those experiments, so there's that boot and the sense of this is the direction that the trench has retreated. Okay, and actually if you look at that cross section, you see a flat-lying slab. So that means, well, there's a viscosity jump there, and this Mediterranean in 30 million years has ripped open a back arc basin, and so there's the current subducting slab, and there's the previous Mediterranean. And then if you look at the Japan Sea is also a giant back arc basin. And what do you see in the tomography there? A nice flat-lying slab. So it's really the combination of trench motions at the surface and this viscosity stratification that give us stagnating slabs. Okay. Well, these may become these are 100 kilometers thick, and they're starting to thermally diffuse away. Their buoyancy is becoming less concentrated, and whether or not they will flush down in the lower mantle is not clear. So I want to show you this is a cross section through that model that I showed earlier, just at the symmetry wall. And you see we get a nice flat-lying slab resting on a viscosity interface just because of the trench retreat. 100. It's meant to encapsulate other things, including that we don't have temperature, so we're trying to also factor in what the retarding aspects of missing the 660 phase change. We're using the Cluse sort of estimate of density for modern Earth, which is 80 or something kilograms per meter cubed. So it accounts for the basalt crust. Okay, so like I said, here's a nice picture. It's very clear this is a 100 kilometer thick slab that's subducting in the upper mantle. But when you get down to the lower mantle, well, these features are 400 to 500 kilometers thick. Okay, but they were just up there. They were 100. And so what happened? They are thickening by a factor of 3 to 5 times. And this is something Quentin mentioned about the mechanical folding. Okay, and this goes back to some old work by Vanderhilst, that if you had a subduction that was stationary, you could develop a little pile, and that pile would eventually kind of flush through. So there's a cross-section of the Marianas Trench where this trench has been quasi-stationary for about 30 million years. And this is some tomography model showing, there is a big blob there that's kind of related to that stationary trench that would have been present for a while. So I want to show you what this slab folding. So there's the slab, and it starts to do this recumbent folding. You can see one pile, there's 3 folds, then it'll go back and do another fold. And so these are the kind of thickening and mechanical folding that can happen at that viscosity interface when this trench is stationary and it's not migrating. Okay, so you develop these little piles. They look very similar. And Neil Reeby has done this with some tank experiments to describe this thickening. So I tend to think of the 660 as a low-pass filter. These things are going to concentrate their buoyancy and also increase the thermal diffusion time. So these big blue features that you see in the bottom of the mantle, they may be present. They may be able to sustain their thermal heterogeneity for a lot longer than what you'd estimate just from a 100 kilometer thick slab, because this is going to have a much larger diffusion time. It's 500 kilometers thick. Like I said, those are the sinking rates, so there's not too much. So that should be diffusion. Yeah. Of piling, and then eventually flushing down as a larger instability. So that's what I mean by a low-pass filter. It's probably some of the flat-lying slabs aren't going to be big enough to go through because they're going to thermally diffuse, and then their buoyancy is scattered across a large region, and then these you're concentrating and piling that buoyancy up and making a nice big thermal heterogeneity that can flush down. Stationary trenches through time. So slab morphology is a function of the viscosity stratification. Slabs have to be weak, and the plate width, whether or not it generates trench retreat or stationary slabs. All right, good. We made it. I want to show you a few of the things that. So in that first slide, I showed a mantle convection model that distinctly had a two-sided symmetric downwelling that was far from what we would call subduction. And a number of those questions I think I posed early on, due to all of these very talented people working hard at doing impressive things, we've answered a lot of them. And it's been a really fun time to be thinking about subduction and seeing all these sort of interesting questions getting resolved. So one thing that we notice now is that, and our models actually had this in there pretty early on, is that these subduction hinges have to be weak. And that doesn't bode well for, early Earth, because the Earth was hotter, so things would probably be even weaker. But again, we've got to factor in what the petrology has to say about that. And so we get that weak brittle crust that helps reduce the size of that strong core. But we still do need a strong core, because we have to be able to allow a mechanism for the slab to pull the trailing plate. And then we have this a free surface on Earth, which is actually a lot harder to model in numerically. So there's been a lot of effort to develop codes and techniques to handle free surfaces. And then finally, this low viscosity wedge, it seems to be critically important in developing one-sided subduction. And we think that wedge is simply the product of dehydration of water-bearing mineral phases reaching pressures that they have their water removed, and it's just pressure driven, and that helps define a nice wet and then lower viscosity wedge. And so there's a really nice review paper I'd put in there that covers even more stuff that I didn't have time to talk about, but that is a nice snapshot of the state of the art in terms of the modeling. So this show a little bit of work about this weak wedge hydration. So they actually include a lot of different. They're trying to include petrology here, and so these are high-resolution 2D models, but they're including petrology and melting and sediments. You've got different. So there's the oceanic crust, the basalt. You've got quenched mantle, different melting relationships, and a background asthenosphere. And then you get they have mineral phases in there that will hydrate the mantle, and this actually feeds back into the viscosity. And so there is in these models a viscosity feedback here from the hydration, and that develops and allows that hydrated wedge to form. And you actually, if you don't have that, you won't get one-sided asymmetric subduction. So that's critically important to how Earth plate tectonics works. It's just as soon as you can subduct something down there that has some water, you can develop that wedge. And that wedge will then allow one-sided subduction to continue. In this case, a slab rollback for these models. So a little bit of weak spot there, and the negatively buoyant slab will start to subduct. In this case, you're going to have a back arc basin develop, and the number of features in this model is ridiculous. So the slab is spontaneously bending. There's erosion happening and sedimentation that's feeding in to the accretionary prism. There's viscoplastic, temperature, stress-dependent rheology in here. There's the slab dehydration coming up, and fluid flux, decompression melting. So here's some decompression melting that's allowing a mid-ocean ridge, back arc basin volcanism to get. And then they actually try to account for some crustal growth. And now, since this plate was broken, there's less stress to maintain that upper surface boundary, and so the plate begins to roll back. So we've got all the elements of a real Earth-like looking subduction zone that would develop Earth-like plate tectonics. And there's a 40 million years. I think that I think it's ran out of plate. Yeah. So this is 2010, and they've been adding more and more things in there. But this is like the result of sort of a decade of work, and they can develop. So this is in a continental setting. In the continental setting, they get some kind of melting in here. So these are all the different phases that are in there, and you can look at this talk and start to look in more detail. That they're able. It's amazing they're able to incorporate all of these different phases. And in here, they actually have intrusive rocks and a sort of arc roots. So there's actually intrusive rocks getting formed in these models, and so in this scenario here, it's developing some. So you've got molten sediments and all kinds of mixed up things in there. So I'd point you to this paper here, which has just come out, and then also for this model setup, the development of a spreading center inside of originally a continental setting. So a huge variety of behavior that seems to now incorporate all the petrologic aspects that are going on. At least we're beginning to get there. This is far from perfect as far as the petrology goes, but to do the stuff on this scale and to bridge those scales, it's really a matter of bridging those scales. So this is the first step in that multi-scale problem. And they can measure growth of the crust. The other direction to go in is to take all of the slabs that we have in the Earth, and then put them into spherical geometry and try to generate plate motions ab initio just from the density structures that are there. And if you account for all of the different types of viscosity and very fine plate boundaries, and there's that Tonga Kermadec, you can generate some fast retreat velocities that vary along there, and also self-consistent sort of retreat directions in the other way along the New Hebrides. So you can recover a good amount of the plate motions just from putting the density structure of the Earth in and letting it go. And so this is a sort of a state-of-the-art model, the Caltech group working with Texas A&M.
Dave, actually the flow around the edge of the slab of the northern terminus of the Tonga Trench is going in the opposite direction that you were suggesting.
No, it's going there.
There are arrows in northern Law Basin going northeast.
Oh, where you mean?
Plate velocities, or
These are plate velocities.
not the maximum?
Yeah, these are plate velocities. The other exciting development is having one-sided subduction and global mantle convection models happen spontaneously, which is strongly asymmetric and has migrating downwellings. And so this is really driven by this innovation of getting a free surface into the models. And so if you look at this model, this is a subducting slab. It's got a high viscosity because it's red, and it is retreating over time. This is time. So looking at that, it's asymmetric and it's retreating. So you have slab rollback in these models and asymmetric and nice. So if you watch these over time, there's some nice movies. You see things really analogous to Earth-like plate motions and asymmetric migrating downwellings.
In these kinds of models, what is determining the width? Because that's crucial to the rollback, right?
Yes.
Does that emerge from the
That's
model
emergent.
naturally?
It's emergent, yeah. Yeah, they have a convective system that sort of naturally decides a width, and so they.
Or whole mantle convection?
Yeah. Yeah.
Is it a big deal that they don't have a 660 kind of stagnation?
Well, they do in some places, but they actually are driving the system pretty hard. So they're it's probably strongly. I mean, these there's no ponding or anything like I showed you. So these, yeah, these plates are probably a little bit bigger than they could be, but I think the system's driven pretty hard. So this system actually, if you let it run for a short amount of time, it actually locks up into a stagnant lid. So this is an ephemeral. It's a bit of a cheat. So this is an ephemeral part of a as the planet cools off, these things start to slow down. So we got more work to do. Okay.
So it's an early Venus.
It could be an early Venus, yeah. And then finally, I'll say that just something in my own group here is doing. We're looking at the influence of this decoupling, and so if we don't actually have a self-consistent low viscosity wedge generated by a slab dehydration, but we're just trying to, in general, include for some amount of decoupling between the overriding thermoboundary layer and this thermoboundary layer. And just by changing the original extent of the decoupling, you can generate this giant range of behavior from that two-sided, so you see the boundary layer coming from both sides, and roughly symmetric, just as in the mantle convection model. And just a subtle change here, you end up with a asymmetric, but still two-sided subduction. And then with a little bit more decoupling, the system's able to develop and maintain a nice corner flow here in this case, and maintain that decoupling. Otherwise, the diffusion here, thermal diffusion, acts to destroy the circulation. So you need to have a continual replenishment of low viscosity material, either through circulation or through injection of hydrous material. And then if we have that, we can have sort of asymmetric one-sided subduction. So, but these things are all possible for the early Earth or for other periods in the Earth. And so I think I will end there. Yeah, we made it. Okay. Ed.
Oh, you're getting sick of me. So this arcuate business, I was curious, in your the movie you showed with the wider slab, it almost seemed like, this is why I asked you what happens if you keep going, it almost seemed like it was the map view that the trench was fairly linear with an arcuate edge to it. Is that a morphology that you might see for some rheologies, but Earth just isn't in that place right now? Or was I misinterpreting the...
I think we were trying to argue that had elements of a few subduction zones on Earth, like Sumatra. Sumatra has kind of a, it's curved around the arc, but then out in the Andaman, it's got a little bit of trench curvature, and then out in like Timor area, there's a little bit of curvature. So it's sort of a quasi-stationary, straight central portion, and then curved edges. So that's what we were trying to make an analogy with.
But you end up with calculations where it's not curved, with more curve at the edges. It's sort of straight with kind of curving at the end.
Yeah, the curving at the end is yeah, I think it's because we're missing neighboring plates. Yeah. Yeah, they're basically crude models, so we're only like making, we're only getting part of what we need. Michael?
Dave, every now and then people try to shield towards slab here, which is related to volcanism in unusual places.
Yeah.
Does that affect the curvature? And could you use the observations of curvature to test the hypothesis?
Okay, do you mean lateral tears, or do you mean detachments, like full-on
People talk about slab windows.
slab windows?
Slabs that are torn, which makes them
Right. I think that, well, I'll cover this in the research talk next week. The famous slab window development is the one under California that generated the San Andreas Fault. And what we think happened there is once that window got big enough, so the trench curvature in this case, because the plate is subducting under a big continent, the continent is dominant in deciding what the curvature is, right? But at the same time, we had a wide slab that was all along North America, and then it was cut in half. And so what happened was you had a wide plate that wanted to subduct through forward plate motion, and then this slab tear, once it got big enough to allow enough mantle flow, it got broken into two narrow plates that wanted to retreat. And so that slab tear led to some interesting changes in the partitioning of those plates themselves, and that segmentation. We think that's what led to the Juan de Fuca plate starting to become more focused in rollback, and we argued that that's the driving force behind developing the basin and range. So, as far as you mean looking at attikites and things like that, as windows into where these, I think that could be useful in terms of mapping out where the edges of slabs are. It seems like I've seen a few stories that held up. They seem to make sense. Yeah, Doug?
Yeah, in terms of the effect of hydration on the weakening of the system, allow. A lot of times we think of just the overriding plate and the hydration of that and the interface, but are you also talking about the hydration of the downgoing plate itself? Serpentinization of the upper part of the slab, which would increase the volume of the material and so forth.
Okay, I'm aware of a couple of studies that tried to look at that in terms of how much. I think one study indicated that they wanted some serpentinized material to be also contributing to the amount of dewatering into the wedge. So you're talking about the volume of hydrous material going into the wedge, whether it's just from sediments or whether serpentinized material is contributing?
Yeah, but I mean, if you have faults, say, at the outer rise or trench, and you serpentinize along those faults, then the upper mantle material of the plate the volume will expand, and whether that also helps with the bending plate.
I think that there were. So the question is whether or not outer rise faults allow water to penetrate deeper into the lithosphere, and I guess I would agree with what you weren't here, but Bruce made a comment that the plate has to break initially in order to let the fluid through, and if it's broken already, then if it's broken and hydrated, it's already weak. If it's broken and hydrated, it's just still weak. But I think it's important in terms of the whole water cycle. Yeah, okay. I'm being moderated, so.